Good morning. Welcome to the first keynote session for today. It's my pleasure to introduce my mentor, good colleague, as well as a good friend, Prof. Tianzi Jiang. Prof. Jiang is director of Beijing K Laboratory of Brainnetome, director of Brainnetome Center, the Institute of Automation of Chinese Academy of Sciences. He's also a core member of the CAI Center for Excellence in Brain Science and Intelligence Technology, and professor of Queensland Brain Institute. Prof. Jiang received National Natural Science Award of China and Changjiang Professorship. Recently, Prof. Jiang was elected as Fellow of American Institute of Biological Medicine and Biological Engineering. His study on human brain connectome atlas was ranked the top 10 breakthrough in science, technology, as well as medicine of China in 2016. It is also ranked the top 40 milestone achievements of Chinese Academy of Sciences in last 40 years. Today, Prof. Jiang will share with us on this research, the human brain connectome atlas and its application in understanding brain function and disorder. Please join me to welcome Prof. Jiang.
Okay, thanks, Anqi. Also, thanks to scientific committee to give a chance for me to share some idea in this community. So, in fact, today I talk about the atlas called the Human Brainnetome Atlas. So, I think this atlas is different from the existing one. So, in fact, besides the postulation for all the atlas, so I think this also includes the connectivity atlas. So here, so I just told you what is the Brainnetome atlas. So this is the fine-grained postulation plus the connectivity atlas. So I think in future, so one brain region is how to connect with other parts. So this is essential. So especially to understand the brain function and also disorders. So in this talk, I will show you how to construct the Brainnetome atlas and how to evaluate the reliability of this atlas and how to apply this kind of atlas to address different issues from different fields. For example, from neuroscience and from the clinical practice or this kind of things. So in fact, what is the Brainnetome? In fact, I wrote the papers in 2013. So give a very detailed description for this kind of stuff. So in summary, so Brainnetome is just consists of two basic components. One is load, another one is the connection. So but the Brainnetome can be studied on different scale. For example, we can on the micro scale, massive scale, or massive scale. So in fact, for example, on the micro scale, we can take a neuron as the loaders and the cerebral connection as the connection. So why we always invest these two parts, for example, on the micro scale. So how identify the cell types of neuron? So this is a very big challenge. For example, in the United Brain Initiative, so this is put on the first topic to studies. But in China, in future, so the China Brain Project also put this kind of things on the first research topic. I think this is very important. But on the massive scale, this is also very difficult to define the loaders. So today, I just try to show you, especially on the macro scale, especially use the neuroimaging to identify the different loaders. So in fact, here, so a lot of very extended study use different technology for postulation. I think postulation is just one story. I think a larger story is connectivity atlas. So this is why, of course, the Brainnetome atlas. So in fact, for the Brainnetome, I think at least includes 4 to 5 different research topics. So first one is how to construct the brain network tomography. So this you can use different technology to construct, for example, functional networks, so atomic connectivity and also networks. So we cause some kind of things just means the Brainnetome atlas maybe plus the connectome, these kind of things. So another important topic is on the dynamic case. So for example, for one network, so how we change on different states, for example, from one state to another one. For example, in the morning or in the evening, so the same network is the same or different. If one takes a drug, so before and after, so this is the same or different. So all these kind of things causes the dynamics and the characteristics of networks. So the third one is the network manifestation of function and the malfunctions. So of the brain. So in fact, this is a very big research topic. So the first one is about the genetic basis of the brain networks. So in fact, the fifth one is related to computing. So we call the simulating and modeling of brain networks on supercomputing facility. So in fact, for example, the Human Brain Project in Europe, a lot of topics just focus on this kind of field. So now I come back to the atlas. So in fact, for the atlas, have a well-known histories. For example, so now a lot of people use the Brainnetome atlas. In fact, especially in clinical applications. So a lot of doctors use this kind of. So as you know, this is a very rough atlas. For example, just include the 52 different parts for the cortex. But I think there were several milestones. So here I especially match the U-brain. So U-brain just takes the same idea. So just based on the SAT architecture to pass the brain into different parts. But as you know, now the technology is much better than 100 years ago. So a lot of brain regions can be passed into different sub-regions. So I think so far, this have a lot of finish. I mean, so this is a lot of full brain atlas. So in fact, for Brainnetome atlas, this is take a very different idea. So we just from the imaging. So as you know, for brain imaging is very different from any other imaging. Why? So because for brain imaging, each works, we can define the connectivity profile with other parts of brain. So for example, we can use the functional MR to define the functional connectivity profile. We can use the diffusion MR to define the anatomic connectivity profile. So this is very different. So this is maybe essential for the passage of the brain into different parts. Also, this can be done in vivo. So here, we just take this kind of idea. So now I move to how to construct this kind of atlas. So this is not so difficult, but we first should go to T1 images and also diffusion MR. So just these two things, we can construct our atlas. So anyway, if we want to validate this kind of atlas, we can also connect some other modality, for example, functional MR, especially in resting. So I don't want to go through the full pipeline. I just give you some examples. So first one is some regions with heterogeneous SAT architecture, such as these regions we call the post-medial cortex. So this is very complicated. So include different type of SAT architecture. So this is not any problem if we pass this kind of regions with the SAT architecture. But here I just try to show you, we can also pass this kind of regions into different parts. Here I show you can be passed these regions into 5 different regions. More important, so if we use the anatomical connectivity profile to pass this kind of regions, we can also provide you with the connectivity profile. So for each sub-regions. So this is, provide you more information than the SAT architecture. So for SAT architecture, you just provide you the passation. But for the, you use the connectivity profile, we can provide you the connectivity atlas. So in fact, so I have mentioned before, for 5 different regions, here I show you 5 different connectivity profile. So another example is for some regions. So for example, for temporal pole. So for this kind of regions with homogeneous SATA architecture. So for this kind of regions, if we use the SATA architecture to pass this kind of region, this is very, very difficult. So because the SATA architecture is homogeneous. So but use the connectivity profile, you can also pass this kind of regions into different paths. More important, we can also provide you the connectivity profile. So for each subregions. So here I just show you, this is the fingerprint for 3 different subregions. So from here you will find this is very different. So we can also provide you with the connectivity, functional connectivity profile, just the computer use the resting functional map. So in fact, before we construct the full brain atlas, we should validate the method on different regions. So in fact, this is a big challenge because different regions always we should use some different information. So we just, for example, for some regions like the motor areas, so we just use the local connectivity profile. We can pass the brain into different paths. But for some associated cortex, so if you just use the local connectivity profile, so the result is very terrible. So we should use the full brain connectivity profile. So far, we finished the full brain passation. So subcortex and subcortex. We passed the cortex into 210 different parts, and the subcortex into 36 different parts of subregions. So totally, this atlas includes 246 different parts. Besides, as I mentioned before, besides this kind of passation, we also provide you the connectivity atlas. So just means for each subregions, you can go to what kind of other regions connected with this kind of region. So from here, you will got a very clear idea. So in fact, besides we provide you this kind of atlas, we also provide you the software. So how to use this kind of atlas to address different issues. So in fact, you can very easy to go to the website of this kind of atlas. So in fact, a lot of popular software, for example, for SPM and so on. So you can very easy to find integrated this kind of atlas there. So you can just use for address your own issues. So now I move to another part of this talk. So how to evaluate the reliability of this kind of atlas? So in fact, we from 3 aspects to evaluate this kind of atlas. So first of all, just use different modality. For example, we pass one regions, use allotopic connectivity profile, then we can compare it with SATA architecture. So if this kind of regions can be passed with the SATA architecture. So here I just show you some examples. Sorry, too quick. So for example, for broken arrays has been passed into different parts a very long time ago. But here, we use the allotopic connectivity, also pass that into different parts. We can compare. So the result is the same or different. I mean, it's just for passation. So from here, you will find the result is very high consistent. So from the tomography. So because for the SATA architecture, we have low the connectivity profile. So we just compare the tomography is fine. So also for some other regions, we can also find it. So the consistency is very high. So besides the cortex or subcortex, we can also find a very high consistency. So here I show you, besides just compare directly, we can also use different modality. For example, we can use allotopic connectivity profile, pass it one regions, so then confirm use the resting or some other. For example, for this one, we use 3 different, so this is use differential MR to pass these regions into 5 different subregions, so then use the resting. From here you will find the result is very similar. So then we can also use the co-activation to confirm it. So here just means uses multimodality. We can also evaluate this kind of pacillation. So the third one is a little bit different. Not just confirm the pacillation, we can also confirm the function. For example, this is about the vertical areas. So in fact, so far, no one can tell you exactly where is the boundary of vertical areas. So in fact, different people always have different idea. So here, we just take what's the vertical areas. So some people think this, some people think this one. So we put together. So then we pass it into different parts. So we find the posterior boundary is very clear. So for example, here we pass the big vertical areas into 3 different parts. So the anterior, posterior, and the posterior. So we find, so use the intraoperative electronic stimulation. So this is this kind of data can only get from the neurosurgery. So when we stimulate the first one and the second one, so this is related to language. So the language will be changed. So, but if we stimulate the third one, so I mean the posterior, so no any change on the language. So this means this part is just related to language. So we can also use this kind of technology to evaluate the function. So here, just the start. So a lot of study just underway. So I have mentioned before, we can also, besides the cortex, we can also try to evaluate the subcortex. For example, for the nuclear accumbens. So in fact, the traditionally always pass it into the shell and the core. So these 2 parts. But it uses the connectivity profile. We can also pass it 2 different parts. The result is very similar. We use 3 different modality to pass it these regions. So the result is very consistent. So this is the fingerprint. I don't want to match more. So now I move to another way how to evaluate the pacillation. So in fact, so in the first part of validation, so I told you, for 1 billion regions, we can pacillate you different modality or different approach, so, but we can get the same result. So why? So I think this kind of pattern maybe is interesting. How to prove this kind of idea? So we use the twin study. So in fact, from the animal study, there are a lot of very excellent results. Told you this kind of pattern modulated by the different gene. So for example, even on the human study, so we also find 3 very excellent study. So first, just pass the cortex into 4 different parts, just based on the you use the twin study. So I mean the genetic correlation. So then it also passes into 12 different parts. But in that studies, so level touch. So for some specific lobes, for example, for some specific regions, if this kind of method can be used for evaluating the pacillation, but no any answer for this. But here we try to address this kind of issues. So this is a pipeline for these studies. So first we should collect the twin data. So then we also compute the cortex areas. So first should divide it into different triangle. So just use triangle areas as the genotype. So then we use the addiction gene and environment model. So then we got a matrix. We call it the genetic correlation matrix. So based on this kind of matrix, we can pass the different parts of brain, so into different subregions. So here I show you 4 examples. So what's this kind of regions? We have passed it with the anatomical connectivity profile. So from here, we best use the genetic correlation. We can also get the very similar result. So here, so this is a supermedia from the cortex or from the paw, or what's this kind of publication. So then, especially for the primary motor cortex, so because they have a topography, so for this kind of things, you have a very good correspondence. So here I just try to show you, use this kind of methodology, we can confirm the genetic basis of the Brainnetome atlas. So now we try to show you one more examples to how to confirm the reliability of the Brainnetome atlas. So for example, so I think the connectivity determines the function. So this is not just from mine. A lot of people think so. So how to approve this kind of things? So in fact, the first study just uses the atomic connectivity profile to predict the phase selected in the fusion gyros. So, but fusion gyros is a very simple function. But for some very difficult, for example, for prefrontal cortex, this is very complicated. So for example, for the work memory or this kind of things. So if this kind of method also can be used to study this kind of issues. So this is the first question. So whether atomic connectivity profile can predict the functional activation across different cognitive domain, I mean the whole brain. So if we use this kind of a method to do this kind of things. So if this question is yes, so what is different for different regions? For example, prediction is brain the prefrontal function or predict some other parts. Is the same or different? So this is the two questions. So in order to address the first questions, so just predict other parts of brain. So we use the HCP data, and also I don't want to go through the details. So in fact, from HCP, we have 7 different tasks. So if we use the atomic connectivity profile to predict each task from here, so the result is, the answer is yes. So for example, so the first column is the predicted activation. The second one is the actual activation. So in fact, the result is very similar. This one is the prediction. This one is the actual action. So the result is very similar. So in fact, we have also the quantify. So how similar? So this is the. So when we answer the first question, so the following question is easy. Is different. So how to quantify this kind of prediction accuracy? So we defined the connectivity function relationship as the quantity. So use this kind of things. We try to find what is the distribution of the full brain. So here we show I think a very interesting result. So we can also use the Thomas Yau's the passation, just the cortex, we can divide it into 7 different networks. Some is related to vision or auditory or related to some other high function. So from here you will find, so if a cortex is very simple, just as the visual cortex or audio cortex, so the prediction accuracy, the CFR, means the connective function relationship, is very high. So for some regions, for example, especially for some prefrontal cortex, so the CFR is low. So, but this is represent a hierarchical pattern. So for different tasks from here, you will find all have this kind of hierarchy distributions. So more interesting. So in fact, we find a lot of other hierarchy. For example, for mining, for functional flexibility, for functional variability, also have this kind of pattern. But for the connectivity functional relationship hierarchy, have a very strong relationship with this kind of hierarchy. For example, with the mining, so have a positive correlation. With the functional flexibility and the functional variability have the negative correlation. So this is very interesting. So now I move to how to apply this kind of atlas to address different issues. So first one is about the parallel hippocampus. So in fact, so for Alzheimer's disease, so now only the medial temporal pole. So for this kind of things, can be used as an assistant diagnosis. So, but the medial temporal is very big, include different parts. For example, parahippocampus. Why we choose the parahippocampus as examples? Because there is a hypothesis for episode memory. So one is a posterior memory system, another one is anterior memory system. So what is the anterior memory system? Just the anterior parts of hippocampus, so with some other regions, so consists the network. So this kind of network causes the anterior system. So another one causes the posterior. So, but a lot of functional study, so is inconsistent with this kind of hypothesis. So even this model published on the Nature Review Neuroscience, but a lot of study is inconsistent. So we try to confirm this issue. Maybe there are new regions between the anterior and posterior. So we also use the anatomical connectivity profile to pass out the parahippocampus into 3 different parts. We found the middle part is different from the anterior and also different from the posterior. So this means there is a transition areas for the hippocampus. So based on this kind of finding, so the existing model should be revised. So for example, we should use this kind of the pathway to describe the memory systems. So more interesting. So we also try use this kind of things to figure out the Alzheimer's disease. As you know, for example, become 10 years or 5 years ago, before they become Alzheimer's disease. So in fact, some parts of hippocampus will be damaged. For example, the early is the anterior and then to medial and then to the posterior. So when one person becomes Alzheimer's disease, the full hippocampus will be damaged. But if maybe 10 years ago or 5 years ago, you will find maybe there was some dynamic things included this kind of things. So another example is about the depression. So in fact, in the hospital, so the numbers of depression, so especially male, is very much less than female. So why? So no one can tell you. So here we just try to figure out this kind of issues. So in fact, we just take as a university student, we collect the emotion regulation score and also the image data, anatomic image, diffusion MR, functional MR, all these kind of things. So as you know, the emotion regulation is a main symptom of depression. So what kind of network is related to the emotion regulation? So in fact, we found that one is the amygdala. So we just take amygdala as the center region. We then compute the connectivity strength with the other parts of the brain. So then we compute the correlation between the connectivity strength and the emotion regulation score. So if we just take amygdala as one city, so last I can find between the male and the female. But we can use the new atlas. New atlas passes the amygdala into 3 different parts. So especially the marked with the red color, so we call the central media. So for this part, we have some very interesting things. For example, for the connectivity between the central media and the medial superfrontal gyrus. So this kind of is here. So we call the cognition-related networks. So in male, the correlation is positive. In female, is negative. So male and female show a very different pattern. So on the other side, so for some other regions, for example, between the central media and insular and also temporal gyrus, So for this kind of network, we call the emotion regulation networks. So in male is negative, but in female, this kind of correlation is positive. So this is means male and female use two very different network for emotion regulation. So if you just use the old atlas, nothing you can find. This is also tell you, maybe use the new atlas, you can find a lot of new things. You use the old atlas, you cannot find. So in fact, much more important, we try to use this kind of atlas for the therapy or diagnosis. So for example, here I just show you one example. So for some therapy, especially use neuromodulation stimulation. So in fact, for the Parkinson's disease, here a lot of people touch this kind of things. So the STN is a target field, but for this kind of field is very big. So in fact, include 3 different parts. So one is related to the motor, another one is related to the emotion. So the third one is related to social cognition. So if you put the electrode stimulations on the motor, so for Parkinson's disease, maybe it can be improve the therapy. But if we put the doctor put the electrode stimulation on some parts related to emotion, so maybe this is disaster. So it does not improve the therapy, but also maybe cause some other problem. So this is, for example, now a lot of studies just underway. So for example, for TMS, you should try to find the target where. So but use this kind of atlas, maybe can tell you where is best. So I mean some evidence-based therapy. So also for the disorder of conscience, so now some study in my group is also just underway. So this is very powerful to tell the doctor so how to use this kind of things. So another one is for the trauma. So this is conducted also in a hospital. So they use MRI-guided ultrasound stimulation. So they also need to confirm for which one maybe is best for the therapy. So I think use Brainnetome atlas can help a doctor to do this kind of things. So in fact, for the diagnosis now, there are a lot of, the pilot study, so published on different journals. I don't want to mention much more this kind of things. So I'm not sure. Here also have a lot of show the time. How much time? Huh? 10 minutes, okay. So I think I have time. So in fact, for the Brainnetome atlas, so because this is used just the MRI, so we can study on the human, we can also study on the monkey. Because as you know, especially the rhesus monkey, so the structure is very similar to the human brain. So here I just show you one example. For example, I have mentioned before for the neurocarbons. So in fact, for these regions, we can pass that into 2 different parts. One is shell, another one is core. So how about so this study for human, and another one on the monkey? We can also do the same things. We find that the pattern is very similar. If just from the tomography, the pulsation. But we try to ask for the connectivity atlas, is the same or different? So this is a basic question. So in fact, this is a long story. I don't want to go through the method. So we try, first we need to establish the method, how to compare the monkey and the human. So this is a method I just go through. So I just move to the result. So from the connectivity atlas, so monkey and human, so some parts is very different. But for the connectivity, just with the subcorticals, so the monkey and human share the similar the connectivity atlas. But for the corticals, especially orbital frontal corticals, so the connectivity atlas is very different. It's between the monkey and the human. So here I just show you this kind of stories. Okay, here I show you some examples, just some how to use this kind of atlas to address different issues, some from neuroscience, some from critical practice. As I have just mentioned, for example, for stimulation, how to find the target areas. So this is a very powerful atlas. So in summary, here we show you a new atlas. We call it the Brainnetome atlas based connectivity profile and its reliability. We present here. So with this kind of atlas, we can get some insights of the brain function and brand new knowledge on the pathophysiology mechanism of psychiatry and neurology disorders. I have not given very detailed, but a lot of publication on this kind of studies. So I think this opens a new avenue to study the brain and disorders. Here I show you a little bit more. I'll try to give some perspective in this field. So in fact, even for the brain atlas, now we just established with focus on some very special aging, for example, 20 to 29. So you can also study how development affects this kind of atlas, how aging affects this kind of atlas. More important, so now we have got a postulation. So what is the function for each subregions? Because here is 246. So how to evaluate this kind of function? So now one way is just, I have mentioned before, use intraoperative electronical stimulation, so one by one. But this have a lot of limitation. So this depends on the neurosurgery. So they open some regions. Maybe you can also use this kind of operation to confirm some parts of Brainnetome atlas. So another way is very important. So use the SDEG. So SDEG just try to use this kind of technology to find the epilepsy. So which part causes the epilepsy? So they will put some kind of electrode into the brain. So when the electrode keep in the brain, maybe we can do some task. So use this kind of task to confirm some parts of Brainnetome atlas. So what is the function? So this is also somewhere. So I think a much more important story is, so here a lot of things for evaluation just focus on the postulation. I think another story is the connectivity. So in fact, so far, so we just show you the connectivity file is some kind of main fiber bundle. So what happened, especially this is true or not true? So this is a big question. So in fact, besides the Brainnetome atlas itself, we can also apply this kind of atlas to study the brain-inspired computing, for example, for the brain-computer interaction. So in fact, now what's this kind of study just focus on some specific brain regions, just for decoding, then to develop some brain-computer interaction system. So in future, maybe you can use some pathway. So use more brain regions on the same pathway. So then decode a pathway. So then use this kind of information. So should this kind of BCI system is much more accurate. So another one is direction is for the diagnosis or therapy. So I have given some example before. So for example, for Brainnetome atlas itself, I think three aspects is very important. First one is individualized. So for example, if we want to use this kind of atlas for the clinical practice, we should do this kind of things. So maybe in near future, we will release this kind of study. So especially the software. So the last one is multimodality. So the third one is multi-scale. So in fact, here I first try to show you the second story. So I mean, the first story is postulation. The second one is the connectivity atlas. So in fact, for the current Brainnetome atlas, so I mean, maybe course the visual one. So we just focus on some main fiber boundaries. So this bridge is connected with another one. So in fact, for each boundaries, so in fact, we show here. So we can got some sub-boundaries. So just like this. So first we can extract the full brain connectivity profile. So then we can find the different fiber boundaries. So then we can establish a new connectivity, correlation matrix. We call for each, we call streamline, just very similar axon. So for each streamline, we can compute how similar with other parts. So then we can get a matrix. So use this kind of matrix. So then we can do classify again. So here I just show you some examples. For example, for SLF. So for this is a very big fiber boundaries. So in fact, use this kind of method, we can at least parse it into 10 different sub-boundaries. So in fact, in future, the Brainnetome Atlas version 2, so try to address this kind of issues for the full brain. So in fact, we can use this kind of method for singular boundary or any other. So maybe another paper. So if you're interested, I think we have a poster just to discuss this kind of issues. So in fact, besides for the connectivity file, so here I show you some data. So for this kind of things, it looks very beautiful. It is true or not? So we should address this kind of issues. How to address this kind of issues? But in human, it is impossible so far. So, but we can study on the monkey. So as you know, monkey's brain is very similar to human. We first maybe establish the monkey's Brainnetome Atlas, use the diffusion MRI. So we can use the post-mortem, have a very high resolution, about 0.3 millimeter. So then we can go to a macro-scale Brainnetome Atlas. Use this kind of atlas. Maybe move to this one. So use this kind of atlas. So we can inject this retrograde tracer. So one by one. Same way we can go to each regions, how to connectivity with the other parts of brain on massive scale. So then we can compare the massive scale, the connectivity atlas with the macro scale connectivity atlas. So then use this kind of things, we can confirm which one is true, which one is not. So then maybe we can transfer it to the human's connectivity atlas, so confirm which one maybe. So if the method is reliable, I think on human study is also true. So this is some idea. So in fact, especially for monkeys, this is a big project. We can also construct this massive scale atlas on structure. So with this kind of structure connectivity atlas, we can study the function. So for example, we can use a two-photon image or some other image to confirm one by one. So I think this is a very big areas. So I have to stop here. So in fact, a lot of people involved with this kind of study. For example, Professor Lin Zhongfan, Yue Cui, all is on this conference, and also some people from University of Electronic Science and Technology of China in Chengdu, and also some people, for example, Vice President of Tianjin Tianjin Medical University, and also some colleagues from ULISH. So in fact, in ULISH, they just use the main on the study architecture. So we try to compare one by one. So what kind of thing is consistent? So if anything is different. So in fact, find some the different is very difficult. For example, we just study the broken areas. We try to compare the study architecture and the population uses the anatomical connectivity profile. So we find almost is the same. So also same Eichhoff and Savania. So in fact, this kind of study also got a lot of support from Chinese government. For example, the Chinese Academy of Science, the National Foundation of China, and the Minister of Science and Technology of China. So without this kind of support, it is impossible, because this is really a long study, so take about 10 years. So thank you.